We are calling it probability lecture number 23. So we started this probability lecture series 1.5 years back. And not all lectures are on nitty-gritties of probability. Many of them are. So I thought that I'll take advantage of this slot to talk about our multilingual computation journey. And I have given it a slightly dramatic title, Alice in Wonderland. We'll see why. And this talk was delivered recently in Courts Command Conference on 10th January. Okay, so now many of us probably have read this classic by Lewis Carroll, Alice in Wonderland. So this is this little girl, Alice, who gets bored of her studies. Her sister is trying to teach her something, read something to her. But her imagination runs wild and she falls asleep, and in her sleep she visits a very wonderful land. Okay, and the whole book is about the journey of this little girl from one place to another, and there are absolutely classic scenes in that particular story. For example, the story of a Cheshire cat who is seen on the branches of a tree. The cat gradually disappears, but the green remains. Okay, something very astonishing. Then there is a queen, red queen, who keeps running but gets nowhere. And then she says that Alice is wondering as to how this is happening, why this is happening. So red queen says that uh, just to be at a place, you have to continuously keep running. So this statement is also a classic statement. Many of the statements in Alice in Wonderland, Lewis Carroll's work, looking through the no passing through the looking glass or something. Many of these statements are now classic statements of English language. For example, to be at one place you have to run continuously is often used in politics. Okay, so this is a wonderful contribution. Alice in Wonderland, the book is wonderful. So our multilingual journey also has been of similar kind. We have wandered and travel in this wonderful world of many languages. The advantage being we have been working from India, which is a land of diverse languages. So multilingual computation involves, for example, machine translation. We are going to have a project called Bahubhasha translation system very soon, and translation between languages like Konkani and Marathi would be an important task there. Sentiment and emotion analysis in French, for example, could be another example of a multilingual task. Question answering in Tamil, information extraction and information retrieval in Bengali, Turkish. So these are examples of multilingual computation for particular tasks. So there is a task, question answering, for example, and there is a language, which is Tamil. Now, the world is very multilingual, both real and the virtual world. The internet is also full of many different languages. Some interesting statistics: Bing Translator supports 103 languages, Google Translator supports 109 languages, and another 126 are under development. So notice point, Google Translator supports 109 languages. What does supports mean? For Google, it is essentially a matter of collecting large amounts of parallel corpus. Okay, and many times nowadays the effort is also towards completely unsupervised translation system. I'll touch upon this in this particular talk. And it is only a matter of spending money, obtaining such parallel corpus, and harnessing the power of tremendous computing power to create these translation systems. And another 126 are under development. You can see the kind of effort. In India now, Government of India has started this Bahubhasha project. IIT Bombay is also part of it. We are going to create the translation systems for Northeast languages, English and Hindi and Northeast languages, and also 4 Indian languages of Marathi, Bengali, Maithili, and Konkani. We also have substantial task on hand in terms of 8 to 10 languages and linking them through a common platform. Neural machine translation gives you that kind of facility. Now, India is also an extremely multilingual country, and you can see there are these states here. 1,500 languages are spoken in this country, and 22 are constitutionally recognized scheduled languages. Now, the language-wise distribution on the Wikipedia is also quite interesting. English has about 6.4 million articles, corresponding to 54.6 million pages. Okay, German has 2.6 million articles, 7.2 million pages. French has 2.3 million articles and 11.6 million pages, and so on. Chinese has 1.2 million articles and about 6.8 million pages. Arabic also 1.1 million and 7.5 million. What is the status for Indian languages? Urdu has 165,000 articles and about 1 million pages. Hindi has 150,000 articles and about 1.1 million pages, and so on. Gujarati has about 29.7K articles and about 100,000 pages. So this is the status of different languages of the world. European languages definitely are far ahead of our Indian languages. So much so that there is concerted effort from Government of India to expand the content of Wikipedia for Indian languages. And one of those efforts is to use machine translation and translation for doing so. And we again at Bombay is again a part of Wiki translation project of Government of India. Now, those were statistics and numbers. Now we come to the linguistic view of the language diversity in the country. So major Indian languages are divided into Indo-Aryan, Dravidian, Austroasiatic, and Tibeto-Burman, these four categories. Let me first mention Austroasiatic because it has only two representatives, Khasi and Munda. It is interesting that they have considerable geographical separation between these two languages. Khasi is in Meghalaya and Munda is in the Santhal region in Choto Nagpur. There is considerable geographical distance. How come these two languages are from the same family? And Tibeto-Burman, Bodo and Manipuri, both these languages are in the northeastern part of the country. And in Indo-Aryan, we see again three major subdivisions, Shauraseni, Maharashtri, and Magadhi. So Shauraseni is the Western India group of languages, Punjabi, Gujarati, Hindi, Urdu. Maharashtri is Marathi and Konkani, and Eastern India is Assamese, Bengali, Oriya also would fall in this group. Dravidian is South Central Dravidian and South Dravidian. Telugu is South Central Dravidian. Kannada, Tamil, Malayalam belong to South Dravidian. Now, these kind of language trees or language typologies are very, very important. Linguists have painstakingly created this kind of structure for all languages of the world, Okay? And this requires tremendous insight into properties of languages, their morphological, semantic, and syntactic properties to achieve this kind of grouping. Okay, and these are of interest not only for linguists, they are also of great interest for NLP. So, for example, we have seen again and again that within the same family, the translation task and any kind of language navigation task for any problem becomes easier if the two languages are close to each other. Transfer learning, zero-shot learning, few-shot learning, they become more effective if the host language and the target languages are familiarly similar. So this is a very frequently occurring observation. Now, let me recount our journey through a few milestones. So our natural language processing activities started with in 1996 with a major project from United Nations. This is called the UNL project, Universal Networking Language Project, where the United Nations University, a part of the United Nations, had this ambitious goal of linking many languages of the world through a common platform, Universal Networking Language. So this was an interlingual representation, and many of you probably know that interlingual representation is very demanding in terms of complete disambiguation of the source sequence. So our part was linking Hindi with UNL in terms of producing its analyzer and generator. So that led us to see that we need to represent the word meanings very carefully. Fine-grained word meanings need to be represented. That started our efforts on creating Indian language words. We started this in 2000. The information in the bracket are the publications, well-cited publications coming out of such efforts. So Indian language wordnets got created with Hindi as the pivot, and this was reported in LREC 2010. Based on, once the wordnet was created, like any infrastructure and resource that you create, it opens up avenues for new pieces of work. So we did cross-lingual sentiment analysis at that time, which was reported in Polling 2012. And cross-lingual sentiment analysis at that time was not making use of any kind of cross-lingual embedding, which is now very commonplace and has huge potential in the multilingual computing scenario. We made use of linked Indian language wordnets. Multilingual pseudo-relevance feedback in information retrieval. This was reported in very two top fora, SIG-IR and ACL in 2010, where we showed that information retrieval performance can be improved if we pick up the relevance feedback from multiple languages. This was the work of Manoj Chinnakutla, one of our PhD students in the lab. Cross-lingual sentiment analysis was done by Balmurli, another PhD student in the lab. Then multilingual words and disambiguation. Words and disambiguation has remained the holy grail of NLP for a long time. And we had multiple papers reported through the master students and PhD students led by Mitesh Kapra, who was my PhD student at the time. Then we created the first Indian language statistical machine translation system called Shatta Anuvadak. This was 10 Indian languages and one foreign language, which is English. So 11 into 10, 110 pairwise machine translation systems were created. It was reported in LREC 2014. This was work of Abhijit, Anup, Rudra, PhD students in the lab. Then we saw that languages could assist a different pair of languages coming as pivot language. So this was reported in NACL 2015. Raj Dabre was the mainstay. Rudra, Anup, they also were instrumental in this kind of research, pivot language assistance for machine translation. Named entity recognition, mainly Rudra worked on this, reported in ACL 2018. And we always had this interesting and intuitive idea that named entities, once recognized in one language, did not be recognized in other languages. Named entities do not change their form going from one language to another, hardly. Multilingual transliteration, again, Anoop's work. And I'm mentioning mainly PhD students because they lead the effort. But there are umpteen number of BTech, MTech students who contributed to this research. They are all on my link from my publication page. We did interesting pieces of work on code mixed question answering, again multilingual effort, and neural machine translation, which involves many Indian languages. This is mainly work of Jyotsna, Tamali, and Rudramurthy. So this effort is pan-Indian neural machine translation. Currently, Rohit is working on multilingual disfluency correction. English, a machine trained on English disfluent to fluent parallel corpus and applied to Bengali and Marathi, okay, in a completely zero-shot manner. And this publication, this paper is under preparation and will be submitted shortly. Then multilingual aspect-based low resource sentiment and emotion analysis. This is also at least 3 years of work. Pragyanshu, Kunal, they are working on this. The machine is trained on English but applied to Russian, Spanish, Dutch, and Turkish. We are again preparing publication based on this work and submitting to conferences. So this is how our multilingual journey has panned out. You can see that we have considered many languages and many tasks. But surely the bulk of the work is on machine translation. So let me go into some nitty-gritties and nature of natural language processing. All of us know this by now. It is the natural language processing itself is art, science, and technique of making computers understand and generate language. And we also are very familiar with this NLP stack and the three-dimensional view of NLP, namely language, algorithm, and problem. For discussions on multilingual computing, this language, problem, and algorithm view of the situation is important because you have to understand not only the problem task, but also the properties of the language. Now, main challenge of NLP, as you know, is ambiguity. And by now, many of you have seen this example and maybe a little bored if I repeat this today, but I'll do so because I have these phases of latching onto a particular example, okay, that somehow fires my imagination. So last year, the example was Maharashtra reports increased COVID-19 cases. Okay, so this has ambiguity of dependency parsing. So this particular example is illustrative of ambiguity resulting from named entity, non-named entity disambiguation, and also because of code mixing. So this is the WhatsApp conversation between two ladies, Lady A and Lady B. Both of them are native speakers of Bengali, and they use code mixing freely. Lady A says, "Yesterday you told me about a shop that sells artificial jewelry. Ki naam jana?" So BN/BN indicates Bengali string. What did you say the name was? Lady B, NYKAA, Naka. So this is pronounced Naka in Bengali. So Lady A gets offended. What do you mean, madam? Is this the way to talk? Lady B, Kano ki holo? So why? What happened? Okay, the Lady A did not reply. She was angry. Now, what is the problem here really? So Nykaa, NYKAA, Nykaa Fashion is the name of a jewelry shop. And lots of online shopping is done from this jewelry shop by ladies all the time. Okay, but the problem is that this sounds similar to a word Naka in Bengali, which means somebody who feigns ignorance or innocence, and this word has a derogatory sense. Okay, if you say Naka to a Bengali, he or she would get offended. So since the two words sound similar, in one case the word means the shop, Naka Fashion, and in the other case, this is a Bengali derogatory word. This confluence of two situations is giving rise to misunderstanding and miscommunication. Okay, so this is very characteristic of natural language processing and our day-to-day linguistic behavior. And in this particular case, the ambiguity is between named entity, Naika, the name of a shop, and non-named entity, Naka, a Bengali word. And it is the concatenation of circumstances that these two sounds are similar, okay, and giving rise to this kind of ambiguity. Now, ambiguity happens at every layer and for every mode of communication. So much so that many problems in day-to-day life need to be solved using multilingual signals. For example, sarcasm is a well-known problem where multimodality is of great help. So this text, "oh great," is indicative of positive sentiment. But if you look at the facial expression, this indicates negative emotion. So their simultaneous presence indicates sarcasm. Now, we also know that all these multilingual computation and high performance multilingual systems are possible because of this situation. Data plus machine learning many times outperforms human decision making. And that is giving rise to the possibility of scaling up a problem. Okay, and this particular inequality is the case for multilingual NLP. So I'll now go into a few milestones of our journey. I hope my screen is visible and I'm audible. Am I?
So,
Yes,
yes,
sir.
Yes, sir.
Thank you. So I'll go into Indo-WordNet first. So Indo-WordNet, as I said, is Hindi WordNet as the pivot, and many languages of the country linking to this. IIT Bombay was leading this effort, pan-Indian effort. So Urdu WordNet got created in Jawaharlal Nehru University. Sanskrit, Marathi, and Hindi, IIT Bombay created. Dravidian language WordNets, Malayalam, Tamil, Telugu, Kannada, they were created by many uh, different universities in the southern part of the country. Kashmiri University created Kashmiri WordNet, and so on. Now, this WordNet, many of you have seen, but let me illustrate this WordNet through a small, very short demo. Okay, so this is Indo WordNet, and you will see the multilingual nature of this. Let me also combine this with our machine translation system. This is what I do. Yeah. So suppose the lecture today is on multilingual computing. I've never tried this sentence before, and I'm hoping that the translation would come out correctly for English to Marathi. As far as I know, the system is doing well. So now translate this. आज व्याख्यान बहुभाषिक संगणनावर आहे. अच्छा. So I'm not a native speaker of Marathi. Let me see it through Hindi, Marathi to Hindi translation system. This is the work of, again, quite a few generations of our students, currently led by Saurabh, Shivam, Akshay, Rohit. Aman. आज व्याख्यान बहुभाषी कंप्यूटर पर है. अच्छा. Okay. And then suppose I am also not very comfortable with Hindi. I'll go to Hindi to English machine translation system. So this is describing a full circle. English to Marathi, Marathi to Hindi, and then Hindi back to English. Today the lecture is on multilingual computer. I see. So the starting sentence was today's lecture. Oh, I don't know. Today's lecture is on multilingual computing, and we have got to today the lecture is on multilingual computer. Okay, computing has become computer. So this is quite characteristic of neural machine translation. Okay, words can get substituted, and named entities routinely get substituted, leading to sometimes very funny situation. Okay, so now let me see if I can use the WordNet for meanings of words. Hindi, Marathi. This is Vyakhan. Achha, Vyakhan has two senses. One is an address of a religious nature, okay, usually delivered during a church service. And the next sense is a speech that is open to public. He attended a lecture on telecommunication. So these are two senses, and I can see them in other languages too. Okay. Vyakhan. This is the sense, and should be able to see it in Hindi. Marathi. Okay, let me see it in Marathi. Marathi, okay, Hindi. Oops. What is this showing? I can very seamlessly go from one language to another. This is the first sense of Vyakhan. Should be able to see the corresponding Hindi sense. Synset. Yes. So this is Pravachan, okay, for Hindi. And in Bengali, again, this is Pravachan. Punjabi, I think it's Pravachan again. Manipuri, the script is different. It's called Meiti. Tamil, something equivalent to Pravachan. So I can go from one language to another very easily because all these words and their word meanings are interlinked and through Hindi. We can also see hypernymy, So for Hindi, which is Pravachan, Pravachan is a kind of what? So Pravachan is a kind of Vachan, Vani, Boli, and so on. Okay. So this was a very, very major structure which was created, and it was an important milestone in Indian natural language processing. And more importantly, this was completely free for research purposes. Anybody could download the data and use them, which was also pretty new in India at the time. Otherwise, you had to go through many processes, many application forms, etc., needed to be filled for downloading any resource. So I think IIT Bombay was quite responsible for opening up language resources in the country. Okay, so let me proceed in the word network demo. Now this in the word net allowed unsupervised words and disambiguation, okay, which was also reported in 2011. And the idea was the following. So two languages synsets, that is the words having specific meaning, were linked to each other. And there was a very nice, very cute expectation maximization based algorithm, which I'll illustrate into a few minutes. So the notion of ladka, balak, bacha, chora, these are synonyms of a young person, young male person, boy. Okay, and they were linked with the corresponding Marathi synset, mulga, porga, and por. So yeah, Amar is asking what is the size of the Hindu wordnet. The Hindi wordnet has 40,000 synsets. That means meaning units. And each synset has on the average 3 words. So 40,000 into 3, about 1,20,000 words and 40,000 meaning units. So Hindi is the biggest. And if you compare this with English, English has close to 80,000 synsets, about twice the number. And the number of unique words in English would be about 2 lakh in the English word. So French, German, Spanish, they have comparable numbers. Okay. And if you look at other Indian languages, the statistics is there in the Wordnet website for every language. So the smallest, I think, would be Bodo, Manipuri, those Northeast languages. Otherwise, most of the languages have 15 to 20,000 synsets and close to 50,000 to 60,000 words. Okay, so this is the structure of linked meaning units or synsets. Now, there is a very interesting algorithm, expectation maximization based algorithm, which we designed, and this was a best paper candidate, where we give a way of disambiguating the senses for 2 languages. So this is illustrated by an example here, man. So man is a word in Marathi which has at least 2 senses. One of the senses of man is neck, okay, gala. The other sense of man is prestige, samman. So we know that the Watson disambiguation problem probabilistically can be expressed by the following formula. Probability of a particular sense given the word. Okay. Now we can formulate the probability of a sense given the word as the expected count of the sense given by divided by uh, expected count of the word in all possible senses. Okay. And since the senses are linked, okay, man, for example, is linked with Adar and Izzat. It is also linked with Gardan and Gala in Hindi. So I can look upon the expected count to be composed of probability from the Hindi side and the number of times a particular word appears. Okay, so I express the probability for Marathi in terms of the probability for Hindi, and complementarily probability from the Hindi side in terms of probability from the Marathi side. Okay, it becomes a coupled equation where probability of the sense given the word in Marathi is expressed in terms of probability of senses of the corresponding words coming from the linked synset, and the probability of the sense in Hindi side is expressed in terms of the probability of the sense given the words which are linked through the wordnet. Okay, so details are there in the paper. We don't have time for those details also, but it becomes a coupled equation where two probability expressions are linked from two language side, and there is no annotated corpus needed, only the linked in the wordnet structure. So we of course produce the numbers on benchmark data, and we saw that for tourism and health, the F score was in the range of 70s, and this was way ahead of the WordNet first sense, which is a standard benchmark for evaluating any WST system. And if we take the state of the art, then PCL, IWSD self, etc. These were reported state of the art. We were doing better than those pieces of work. Okay, and completely unsupervised systems were giving F score in the range of 9 and 10. Okay, which were far below our figures. And this was made possible because of the Indo-WordNet structure. Okay? And this gave us the first inkling that that languages can help one another. Okay, so one of the themes of multilingual computing in our lab was that languages can help one another. Okay? Resourceless languages can help resource poor languages. So let's see some more examples of this. Indo-WordNet helps Indian language sentiment analysis also. This was reported in NLP 2011. So sentiment analysis, we know, is a task where the sentiment on a particular feature of an object is expressed, and it is held by a particular opinion holder at a particular time. So this 5-tuple definition of sentiment analysis we have seen is quite crucial, so that there is no confusion of who has what opinion about what object. Okay, so this is illustrated by a complicated sentence like this, where the essential idea is that I, as an entity, love another entity called song. My brother likes the cast, director likes the storyline, public like the storyline, and so on. Okay, so these kind of triples are created through entity relationship extraction. So we have seen that when we use WordNet senses for training a machine learning model, not the words, but the WordNet senses, okay, then the accuracy improves from a baseline figure of about 85 to 86. So one might come back and say that isn't this very resource intensive, because you have to have the WordNet of that language. Okay, also you have to have a Watson disambiguation system whose accuracy we know is not very high for most of the languages. So what are you really getting? You're getting only 1 point improvement over the raw corpora based and of course some annotated corpus based performance, which 85 to 86. No, the performance become little more exciting when we go to a zero-shot situation. So remember, at the time, there was no deep learning, no cross-lingual embedding, but transfer learning ideas were in existence for NLP, and the current name for transfer learning is zero-shot learning. So if the training and target language are Marathi, then for that particular domain, we got an accuracy of about 93. If the training data is Hindi and testing is on Marathi, completely zero shot, okay, then the accuracy figure was about 84, which is not very far from the skyline performance, training and target being in the same language. Okay, so this was the result of the Indian language WordNet. So what happened was the machine which had Hindi training data and sense annotated, of course, was replaced. The words were replaced by their senses using a reasonable accuracy words and disambiguation system, and that allowed creating a machine learning model which could do sentiment analysis in a language independent manner, because all it needed was the synset IDs. So we applied it for Marathi without any training data, and this is the performance we got. So that is how we saw the help of Hindi for Marathi for its sentiment analysis. So this is a recurring theme. Now I come to an information retrieval scenario where we know that when a query is asked, the relevant documents are retrieved. And the relevance of the document is the contributing factor for user satisfaction. So user satisfaction depends on the ranking of the document. Relevant pages should come high up in the ranked list of documents. Ranking is a function of coverage, how much of corpus you have indexed. So crawling, okay, how many pages have been crawled. Then coverage also depends on indexing. Indexing depends on stemming, the quality of stemming, how the words have been stemmed, and how they are indexing through the posting list into the document. The ranking depends on correctness of the query processing, and ranking also depends on output presentation, where snippet, which means a short piece of text, is shown. And correctness of query processing depends on stemming, named entity recognition, multi-word expression. Bay of Bengal, for example, the Bay of Bengal, 3 words. These 3 words form a multilingual named entity. If we retrieve documents only on Bay or only based on Bengal, then we will not get the relevant documents for Bay of Bengal. Okay, so these problems are very well-known problems, and we have seen them in our large project on cross-lingual information retrieval, which was running from 2006 to 2010, and it was released also in January 2012. So there were 9 languages involved: Assamese, Bengali, Gujarati, Hindi, Marathi, Odia, Punjabi, Telugu, and Tamil. The picture was this. If I give the Hindi query Tirupati Yatra, then we should be able to see the documents in Hindi and also in English. If the query is in Marathi, then Marathi, Hindi, and English. All the 3 languages documents should be seen. So this was a large effort by Government of India, and IIT Bombay was leading it. So what is well known in information retrieval is that query is very short. Queries need to be expanded. So this is based on what is called pseudo-relevance feedback. You give the query to the search engine, then there is a 2-stage process. In the first stage, it retrieves some documents. So those documents are then processed for keywords, important words coming from those documents. So they are fed back into the query. The query gets expanded this way. And in the next stage, the documents that come up have better rank and better relevance values. So this is a 2-stage process. This is called pseudo-relevance feedback. And this is a well-known idea existing for a long time. What we said is that why not obtain the pseudo-relevance feedback terms not only from the language of the query, but also from other languages. So query is in L1, then translate the query into L2, retrieve the documents in L2, retrieve the documents in L1, and collect keywords from both languages, okay, and feed it into the query and expand the query. So this we showed has a good performance. So model-based feedback MBF is the normal pseudo-relevance feedback situation. Our multilingual pseudo-relevance feedback normally were scoring better than the normal pseudo-relevance feedback on many metrics: map value, precision at 10, precision at 5, GMAP. These are different metrics for performance measures of search engines. So we were scoring over the pseudo-relevance feedback. Okay. So this is a situation where we showed that invoking multilingual computation is helpful. Okay, it can help information retrieval also. And here are some interesting situations. For example, if you give a French query, honorary Oscar for Italian filmmakers. So the information retrieval system was topic drifting. It was also bringing up pages corresponding to an Italian president called Oscar. But this Oscar is in the domain of film. And when we fed English pseudo-relevance terms into the query, okay, after translation, of course, then that topic drift was avoided. And we could get highly relevant pages because of this English feedback coming into the French query. The map value improved from 0.1238 to 0.4324. So we also wanted to see if other languages other than English also could come as assisting language. And indeed so. So for example, for French queries, English improved the performance by 11%, Spanish by 7%, Dutch by 7% again, and so on. German was helped by English, improving the performance by 39%, Spanish by 39%, Dutch also by 36%. Of course, these were all in academic settings, and many of these multilingual pseudo-relevance feedback ideas are indeed exploited by established search engines like Google, Bing, and so on. So this is happening in the current times, but our paper came as a kind of, pioneering paper for multilingual pseudo-relevance feedback. So we tested it for many languages, and one of the most interesting examples is this matrix. So we wanted to see if the source language is L1, which L2 is in the top position in terms of helping the language. So for English, we could see that Spanish was helping English quite a lot. For German, English was helping. For Dutch, again, English was helping. For French, Spanish was helping. And for Spanish, French was the first topmost helping language. So here, the language family behavior was also quite apparent. Spanish, French, Romanian, Italian, and Portuguese, these 5 languages of Europe, belong to what is called the Romance language. Okay, and they share lots of linguistic properties, and therefore it was not very surprising that they were helping each other. Similarly, German, English, and Dutch belong to what is called the Indo-Germanic family, and therefore German, Dutch, and English helping each other also is not a big surprise. A little surprise was this Spanish helping English so much, and that we trace to the fact that Spanish pages outnumbered all languages pages. Okay, of course, all these were done on a benchmark data set coming from TREC, which is a very prestigious forum for evaluating search engine performances. So this kind of multilingual experience was very illuminating for us, and they were published also in very top forum like SIG-IR and ACL. Amar has asked a question. I'll go to it after some time, towards the end maybe. So then in recent times, we have, actually this is published. In recent times, we worked on multilingual and code mixed visual question answering. This was by Deepak Gupta, who was my PhD student in IIT Patna when I was in IIT Patna, co-guided by Asif Iqbal. So here, the goal was to see if we can build a question answering system which is language agnostic. You ask the system question in English, it will answer the question. Ask in Hindi, answer the question. Ask in code mixed language, Aadmi kya sport khel raha hai, it will answer. And the motivation is that multilingual speakers are quite careless about their language, okay? And they also navigate from one language to another, shift from one language to another very frequently. And we wanted to see if this can be done. And of course, the assistance had to be obtained from a supporting picture. Okay, where is this picture? ये तस्वीर कहाँ की है? Um, uh, it's a picture of market. So answer is market. What color are the trees? And of course, the answer is in English, green. So if you ask in English, answer is in English. If you ask in Hindi, answer is in Hindi. If it is code mixed, then it depends on the matrix language, the host language, in which the answer should be given. Again, lots of details there, quite a lot of previous work too. The data set is VQAV 1.0 data set. Okay. And we use this data set to create a multilingual and code mixed visual question answering data set. This has about 250,000 and 121,000 questions in 2 different languages. So the approach is also a no-brainer. There are image-based features which are ingested into the network, and then text-based features. And then final layer is an MLP classifier dense layer, which produces the answer in the language of the matrix language. Okay, so there is question image fusion layer also, and attention layer, which handles the correspondences between different words in the text as well as parts of the image and the text. So this is a very standard kind of figure where the input has 2 compartments, one for one mode, the other for another mode. And if there are 3 modes, speech, text, and vision, then there are 3 compartments from which features are extracted and passed through the network. The final answer coming from the dense layer always. So, so the results showed that we could improve over the state of the art. These are our numbers. Okay, and you can see that it is always better than what is reported in the state of the art. This paper was presented in AACL. Okay, AACL, I think 2021. Okay, so we discussed information retrieval, sentiment analysis in the WordNet as a supporting structure, then visual multilingual question answering. All these are small pieces of work. They have many details, but the bulk of multilinguality is actually handled by machine translation. And since 1996, we have been after this question: can machine translation be made more effective, where many languages help each other? Okay, and machine translation has these paradigms of rule-based MT, example-based MT, statistical MT, and neural MT. And it has been my observation that analysis, analogy, alignment, and attention, these are the 4 keywords or crucial matters for all these paradigms of machine translation. And languages also have what is called divergence. They differ in vocabulary, they differ in structure. So this is also an example which many of you have seen before. This blanket is very soft, is expressed in 4 different ways in the 4 languages of Hindi, Bengali, Marathi, and Manipuri, with slight differences between every pair. So in terms of language divergence, Hindi and Marathi have low divergence. Hindi and Bengali have more. Hindi and Manipuri quite a lot. And Hindi and English, of course, have high divergence. So as I mentioned, in 2014, we were the first group in India to create a statistical machine translation, 110 pairs of translation systems. And we could see, high blue score in the Indo-Aryan group. But Dravidian group had low blue score, and that we trace to the fact that Dravidian languages are very agglutinative. You can form long words by small morphemes. So we understood the importance of subword-based machine translation. And when we did subwording, we found that morphological subwording, that is breaking the words into their morphemes by morphology analysis, improved the all-round performance. For example, Punjabi Gujarati had an improvement of 11.61%. Okay, from the basic score, the blue score being 44.41, and this is an improvement over the basic word-based statistical machine translation. An improvement is 11.61%. In the Dravidian group, the improvement was much more dramatic, noteworthy. So Malayalam Tamil, for example, improved by 22.92. And the absolute blue score of course was low. It was about 8, but this was quite a lot of improvement in terms of percentage. But morphology-based subwording is costly because it requires morphology analyzer, and most languages don't have morphology analyzer. So byte pair encoding-based subwording was used, and there we could see improvement in Malayalam Tamil, for example, by 29%. The blue score improved from 7.99 to 8.4. And in the Indo-Aryan group, of course, there are representatives like Punjabi and Marathi. The blue score was 28.89. So this was a large pan-Indian multilingual machine translation system in the statistical machine translation framework, mainly the work of Anu, Vijay, Rudra, and team. So then we understood the importance of factors, that is case marker, then semantic roles, etc., which are of course expensive NLP proposition, which could assist multilingual machine translation. And there we could improve the blue score and other metrics significantly by making use of factors. Then the next part was cooperative natural language processing. This was pivot-based machine translation. And here, the main idea was that a strong language can help a pair of languages which are weak in terms of resource. So this, the main idea is that suppose I have no translation evidence for Pani to Jal, Hindi to Bengali, but I have Pani to water and then water to Jal through English. So this we can make use of, and this is called triangulation, and that gives rise to what is called the pivot-based machine translation. The theory is worked out in terms of marginalization. So you can introduce as many pivot languages as you want into these probability expressions for statistical machine translation. So we did this, and as I said, there was a case study here. We wanted to have a machine translation system between Mauritian, Creole, and English. There was no machine translation system for this. We introduced French as the helping language or pivot language. And this machine translation system, by the way, now is used in Mauritius, because this was the work of a postdoctoral student who was visiting our lab at the time. And we could improve the blue score to a respectable 25 by introducing French as the pivot assisting language. We observed similar kind of performance improvement for English to Hindi machine translation by introducing many Indian languages as pivoting systems. And we found that Punjabi and Urdu together were helping English to Hindi machine translation quite a lot. So this was another strand of work where, again, the theme of languages helping each other was exploited. Then arrived the era of neural machine translation, encoder-decoder model, and we immediately used neural machine translation for Hindi Marathi, Hindi Punjabi, Punjabi Hindi, Hindi Gujarati, and so on. So this was an experience for last 5 years or so. And we also moved to completely unsupervised neural machine translation. So in ACL 2019, we had a paper which made use of the isometricity property, where language words independent of the language, but having similar meaning, formed cluster of embeddings. So we exploited this, and the denoising and back translation idea were used, by which we could show that there were improvements in French to English, Spanish to English, English to French, English to Spanish, German to English, and English to German. So improvement in performance was by 0.66, 1.48, 0.4381, 6485, and so on. So this happened quite consistently. And qualitatively also, we could see that the output was much better. Anyway, so this was again a multilingual experience involving Indian, European languages, which were taken to Indian languages later. And in recent times, Jyotsna is working on unsupervised neural machine translation with filtering on back translation. So back translation produces what is called the pseudo parallel corpus. And many of the parallel sentences can be of low quality. And this work actually studies how to filter out low quality pairs. Again, we report numbers, which is better than the state of the art. And this was reported in Kohli. The final thing, which is recently accepted, Jyotsna's work with Rudramurthy Tamali, which shows simple measures of bridging lexical divergence can help unsupervised neural machine translation. So Jyotsna can talk about these variations on unsupervised neural machine translation sometime later. But I touched upon these as examples of our continuous ongoing work on multilingual computation. So here, some very simple ideas like script conversion, unsupervised bilingual embedding-based initialization, dictionary word substitution, and then these simple ideas can improve the performance of unsupervised neural machine translation, which makes use of mass pre-training and iterative back translation. So these variations on unsupervised MT neural machine translation, Jyotsna Tamali can speak on sometime. All right, so I'll not go into details of these pieces of work. Let me go into some summarizing remark. But before that, neural Indian language machine translation system, I demonstrated to you through these three tabs. Okay, English to Marathi, Marathi to Hindi, Hindi to English. All these are neural machine translation systems. They have been created by our students, currently being worked on by Akshay, Shivam, Saurav, Rohit, and new students are also joining in this effort. We are a major group in India's pan-Indian neural machine translation effort. So lots of linguistic ideas and innovative ideas are used over and above the neural machine translation system. For example, we inject the phrase table obtained from parallel corpus. Okay, so you construct the phrase table through statistical machine translation and add it to the parallel corpus for training a neural machine translation. So these kind of innovative ideas are used, and we have created pretty effective three language neural machine translation system here, which will eventually become at least 10 languages NMT, Northeast languages plus Konkani, Marathi, Maithili, and Bengali. So here is summary. Multilinguality is surely a reality, and multilingual computation is the need of the hour. We described our journey in multilingual computation, starting with Universal Networking Language Project in the WordNet-based cross-lingual sentiment analysis, multilingual pseudo-relevance feedback, and finally different techniques of low-resource machine translation. Future surely lies in zero-shot, few-shot, and meta-learning involving many languages of the world. And you would have also seen that we do not handle only machine translation. Multilingual computation ideas are also used for question answering, sentiment analysis, words in disambiguation, and so on. So possibly these are steps towards what is called AGI, Artificial General Intelligence. Okay, so this is the summary, and all this work, are in the context of CFIELD, which has been in existence in 2000, and this description is a contribution of many of you people, the students who have been contributing to the research of this lab for a long time. Okay, thank you. So now I thought I saw some questions. So where is the chat box? And somebody read the question from the chat box. Malharji has raised his hand. Malharji?
Yes, my only comment was about the translation um, related to the English sentence, and I wanted to say that from English to Marathi, it's I think very good, excellent translation. There is nothing to point about any mistake or anything. But it is from Marathi to Hindi that is causing some change, some variation.
Really?
So
Oh,
Sanganana
I see.
is getting translated
Oh,
as computer. That is, I think,
I
some.
see.
But
Oh.
from English to Marathi, it's I think perfect.
So Sangarana became Sangarnak. That is why
Yeah,
the problem
yeah,
happened.
yeah.
Okay, okay. Thank you. And size of Indo-Wordnet. Amar, if you go to the Indo-Wordnet website, you will see statistics on the right-hand side for every language. And then you also ask the performance of multi-PRF is measured in terms of retrieval of source language pages. No, the performance of multi-PRF is like any other search engine. You have to compute the map score, precision at 10, precision at 5, and also what is called the geometric map. So the standard metrics are used there. Yeah. Right. Any other question? Okay. So yeah. Yeah, Amar.
Yeah, I think it's first of all, this talk was very informative and very nice talk. It covered a lot, even digest. Uh, I have a quick question, just continuing on what Professor Malhar was talking about, the translation part. So basically, when we say these Indian languages, right? In some sense, these Indian languages are getting. I mean, they're getting. What should I? They're getting adopted over the period of time. Now, what we actually talk in Hindi, which is not the way the proper or formal Hindi is written, right?
Okay.
So when we talk about translation, so these translations, what do you think about it? How whether that should be also accommodated in the translation part, or because when I say translation, generally they come in a very um, uh, Hindi में we say क्लिष्ट translation. काफी
Ah.
difficult sometimes becomes very difficult to even the proper Hindi or proper
Hmm.
Marathi, but generally
Hmm.
we don't use that language to basically communicate.
Hmm.
Now how, what is your vision on that? What do you think about that? How this translation should also evolve in that direction? How people actually are changing, or I don't know.
Hmm.
I don't have any clue, but I'm just putting this in front of you people.
Yeah, interesting point, of course. That if the translation output by the machine is clished. Clished means not very fluent and not very colloquial.
Let me call this like Sanganana.
Mm.
I Am I audible? No.
Yeah, you're
No,
audible.
my network is not good, so if I'm audible or not.
Mm. Yeah, Sangarana, then. Amar, we have lost Amar's voice. Yeah. Meanwhile, does anybody have any other point or question? Ah, okay, Naveen asks, sir, somewhere I read Dravidian languages are agglutinative languages, that is high rate of affixes or morphemes per word. Can you briefly elaborate on this and how this influence Indian machine translation? Yes, yes. Dravidians are very agglutinative, and Marathi is also influenced by Dravidian. Our favorite example is Ghara Samor Chane, Ghar ke samne wale ne. So here Hindi will use 6 to 7 different words or particles. Marathi will join all of them together. Now, the effect of this is that ordinary word-based machine translation for Dravidian languages produces low blue score. We have seen this in our SMT experience. But when you use byte pair encoding, divide them into substrings, and if you have large amount of corpus, then these statistical substrings often correspond to morphological substrings. Okay, So then in such a case, the blue score improves quite a lot. And this is a recurring experience. So agglutinative languages, if we use byte pair encoding followed by neural machine translation, then the blue score is much better compared to what is there for word-based blue score. So Amar, are you back?
Thank you, sir.
Are you back, Amar? No.
Yeah. Sorry, my network was very bad. I don't know. So
Yeah.
So for example, like the word just now you used the sanganana. I mean, it might be for some people it might be very difficult. I mean, people may not be using that word in daily practices. I mean, in Hindi as well, right? Or even in Marathi. I don't know in Marathi, but in Hindi I know people don't use it nowadays.
So your question is how to make the output of machine translation more public acceptable.
Yeah, that's thank you for bringing the right words for it.
Yeah. So how to make it more commonplace and public acceptable. So difficult problem, surely. Now the whole machine learning based machine translation is really dependent so much on the data. And if the data is of that kind of genre where the language is very official with bombastic words and so on, then the translation output also will use those kind of words which give a cliched kind of translation. So the only method is to have, I think, diversity in the data where those kind of commonplace expressions are also used. And by force of their larger number, maybe they will get higher probability values. And then the machine translation output will be more public acceptable. It totally depends on the data. Of course, there is also quite a lot of research these days on post-editing. So post-editing principle is that you incorporate minimal change in the output of the machine translation so that it is acceptable by human users. So when you have Sangarana in Hindi, convert it to computing, maybe in Hindi. So this kind of post-editing effort is also on, and machine learning based post-editing is quite popular these days. Yeah, but difficult problem, surely.
Thanks.
Okay, so I guess we'll now stop the session. We have information extraction work update meeting. So we'll join in another link which Kaveri has sent. Thank you.
So 1 second, sir.
Yeah.
So my network got disrupted. So the host connection control came back to you. So you'd have to stop the recording for it.
So what should I do?
Do you see the
stop
recording?
the recording.
Yeah.
Okay. Recording is in progress. Open the doors. Now stop. I should say stop, right?
Sir, yes.
Yeah.
That's it.
Yeah, stopped recording.
Okay, sir. Thank you.